Hello, I'm Ross Nakatsuji, Headwall Photonics Marketing Communications Manager. This short presentation provides an overview of NASA's and the NOAA, National Oceanic and Atmospheric Administration's, use of headwall sensors to monitor the environment. Yes, we only have one Earth, so we really should take care of it. And how do we assess the condition of this planet? Remote sensing provides data that we need to make what could be difficult decisions now and in the future. A derivative of remote sensing is remote sensing change detection, sometimes abbreviated as RSCD. This is a process of identifying and monitoring changes between scenes of the same location over time. Sometimes change can only be accurately quantified over long periods of time. You can see that over a period of 35 years, we've seen noticeable changes to Arctic ice fields. That brings us to Operation IceBridge, an 11-year project with over 1,000 missions to measure the thickness of sea ice, glaciers, and ice sheets. Part of IceBridge's value was as a bridge between ICESat-1 and ICESat-2, ensuring an uninterrupted flow of data collection. In addition, flights directly under the orbital path of the newly launched ICESat-2 will help validate measurements from this satellite. Part of the IceBridge aircraft instrument payload is a headwall co-aligned veneer SWIR sensor that was originally designed for lower altitude imaging with drones. A nano hyperspec veneer sensor was first used for proof of concept flights before the co-aligned sensor was installed. Preliminary results showed that hyperspectral data could be used to measure the depth of superglacial lakes. These bodies of water atop glacier ice can be substantial in size and several meters deep. It's thought that they can contribute to the breakup of ice shelves. Operation IceBridge officially ended in late 2019, and its resources will be reallocated. But the data lives on and will continue to be analyzed and utilized for years to come. Here are some pictures sent to us by Program Manager Jim Youngle in the upper left. Clockwise from him, you see a gear falcon, Falco rusticolis, the largest falcon species that breeds in Arctic coasts and tundra. A spectacular photo of colleague Kyle Crable on top of Dundas Mountain, an overflight of a glacier flow, and finally a snapshot of Thule Air Base in Greenland that supported many of these missions. So on to solar-induced fluorescence, or SIF. The first recorded observation of this phenomenon was made almost 2 centuries ago by Sir David Brewster, a Scottish preacher, who discovered that a beam of sunlight striking a green alcoholic extract of laurel leaves elicited a brilliant red light. Professor G.G. Stokes later coined the term fluorescence to describe this phenomena in general. Remote sensing of SIF is rapidly advancing as a technique in agricultural and environmental science, although it is founded upon decades of research, applications, and sensor developments. SIF can be measured remotely using high-resolution spectral sensors in tandem with state-of-the-art algorithms to distinguish the emission from reflected and/or scattered light. 2 photosystems are involved, PS1, which emits mainly in the far red, and PS2, which emits in both the red and the far red regions of the spectrum. Plant reactions to stresses result in changes to the fluorescence emission and reflect a complex relationship between fluorescence and carbon assimilation. There are many benefits to using SIF as a proxy in order to assess the health of plants. Abnormal variations of the SIF signal may be detectable long before signs of stress or damage appear to conventional cameras. This brings us to the SIF imaging sensor, designed and built specifically to measure this useful but challenging signal. What's so challenging about measuring SIF? Well, by the time fluorescence emission reaches a remote sensor in the air or in space, it has been subjected to the influences of the surrounding environment and atmosphere. The light is subject to absorption, reabsorption, and scattering. Disentangling these effects is a focus of interpretation of the fluorescence data, and of course is relevant to the usage of fluorescence as an optical proxy for photosynthesis and associated stress effects. So the design, manufacture, testing, and validation of a sensor to detect this relatively weak signal is extremely important. NASA Goddard helped with both the performance specs needed as well as a testing of the completed instrument to ensure that it met or exceeded the specifications required. NASA calls their sensor Firefly for fluorescence imaging of red and far red light yield. Here's a table showing only a few of the many topics that scientists are studying using SIF. Notice that surveys from the air or from the field have fewer drawbacks or disadvantages compared with surveys from space or from inside greenhouses. Many researchers study forest canopies using tools such as handheld instruments, observation towers, drones, manned aircraft, and satellites. Headwall SIF sensor can be utilized on tripods, towers, as well as onboard manned aircraft. The upcoming launch of the ESA Flex mission provides an opportunity for researchers and for instrumentation that measures SIF, especially in high spatial resolution. The Headwall team that designed and built the first SIF sensor won the prestigious OSA Team Engineering Excellence Award in 2019. Creating and manufacturing a specialized sensor such as the SIF imaging sensor was an enormous task, and the team rose to the challenge. Conventional hyperspectral imaging sensors do not possess the necessary spectral resolution in order to detect the fluorescent signals that researchers need to see. As you can see on the right, the Headwall SIF imaging sensor can distinguish these signals because of its extraordinary high spectral resolution. NASA Goddard independently tested the SIF imaging sensor using their own world-renowned measurement facility. You can see measurements taken by NASA's GLAMOR instrument that show excellent absolute spectral response, the ability to be precisely calibrated, and also a comparison to a well-respected field spectrometer that shows the SIF imaging sensor's very high spectral resolution. NASA Goddard's g-liht manned aircraft remote sensing platform flew over target areas in Puerto Rico and over test plots in the continental US. The instrument was incorporated into a payload pallet as seen in the upper right. G-liht can capture hyperspectral imaging data from the visible to the near infrared, as well as LiDAR, thermal, and high-resolution RGB color images. Headwall is currently working with customers who also wish to deploy the SIF imaging sensor on environmental observation towers around the world. Details such as how the customers protect their instrumentation from the elements and data transfer are being discussed with Headwall now. Thank you very much. If you'd like to know more, you can contact us at sales@headwallphotonics.com, visit our website, or ask one of the Headwall personnel at the workshop today. These following slides provide supplemental information. Here's a link to a very entertaining as well as educational video on SIF. And here is additional data on NASA Goddard g-liht Firefly data.